Okay. So, semi empirical mass formula, what we call the expression of binding energy that you have gotten. Now, by now you must be remembering all those 5 terms. So, can you come here and write all those terms? Yeah, please come fast. Take chalk. Yeah, n minus z. The correction is the second term, surface term, not that. That is all right. The surface term. Correct. Okay, good. Thank you. So, this physical picture you should remember. Okay. If you try to remember when it is a to the power 1 by 3, when it is a and when it is a to power 2 by 3, it's always there is a chance that you will make mistakes. But physical picture if you remember and from there you write, then it will be fine. This is volume term, this we call volume term. It is because the entire volume you have energies. So, therefore, it is proportional to A, right. The volume will be proportional to A, more the nucleons, more the volume, and it is proportional. So, that is this. This is surface. Now, surface is 4 pi r square. Surface is 4 pi r square. Your r is r naught a to the power 1 by 3. So, r square will be a to the power 2 by 3. So, if you can connect this physical aspect, that the second term is coming because of the nucleons on the surface, because they do not have full neighborhood, right. On one side you have nucleons, on other side you have almost no nucleons. So, it is coming from surface, and surface is proportional to r square, and therefore, it is a to the power 2 by 3. Then you will not make mistake. Similarly, here this is Coulomb energy, right, Coulomb energy, and Coulomb energy, Coulomb potential energy is Z1 Z2 E square by 4 pi epsilon naught r. So, it is proportional to 1 by r. It is because the Coulomb energy, right, the Coulomb potential between any two charges Q1 Q2 by 4 pi epsilon naught r separation. So, it is that r, and r goes as 1 by a to the power 1 by 3. Therefore, it is a to the power 1 by 3. So, if you can connect this way, that this is coming from Coulomb potential energy, you will know that it should be a to the power 1 by 3 in the denominator, because potential energy is Q1 Q2 by 4 pi epsilon naught r. Okay. And this is asymmetry. The word asymmetry, what asymmetry? Asymmetry is that number of neutrons is not equal to number of protons, that is the asymmetry. Therefore, it has to be n minus z somewhere, okay. And then your calculation, it is n minus z square and divided by a. Why a? This is because you had all those energy levels, and if there are capital A nucleons, roughly the separation between consecutive energy levels will be proportional to 1 by a, because a nucleons are to be adjusted in that. So, that is why 1 by a, and then this is the pairing term delta. This delta is 0, yes, for odd a nuclei, for odd a nuclei, and this is plus AP a power 3 by 4 for even or odd. Even. This is binding energy. So, for even the pairing is done. So, binding energy increases. So, this is for even. Z is even and N is even, and this is minus AP a power 3 by 4 for odd. Right. Now, the values. So, this is some qualitative arguments and some calculations results in this. Some qualitative argument, it should be proportional to the number of pairs and in the neighborhood, and therefore this, and there are surface nucleons, therefore this, then Coulomb. So, there is some qualitative argument, some calculations also, but it is not very rigorous from very first principle we are driving it, it is not like that. Okay. So, this is known as semi empirical mass formula. Empirical is I have the data and then I fit something without any theoretical background, that is called empirical formula. This is semi empirical formula, because we are indeed doing some physical arguments, we are coming out with some calculations, some theory, some basic theory, but not very rigorously. So, it is semi empirical mass formula. Now, these values A, V, A, S, these constants which are coming, how do we get these values? So, this is an expression which is in terms of capital A, capital Z, N, etc. So, for any N Z, this will give me a value of binding energy provided I know these constants. So, these constants are empirically obtained, fitted from the known binding energies of the nuclei, of large number of nuclei. Binding energies one can calculate, okay. One can measure rather, one can measure because the masses, atomic masses are very accurately measured, and from those atomic masses one can calculate that binding energy. Just take an example. So, I am doing a very basic simple problem. Calculate the binding energy of helium nucleus, that is alpha particle, that is this nucleus 4 He2, and this is also 2, this nucleus. From the following data. This is an example that from the known atomic masses how one gets binding energy, okay. And the data are mass of 1H1, these are atomic masses. 1H1 is hydrogen atom. So, mass of hydrogen atom in its ground state is 1.007825 U. This is a unit, atomic mass unit, I will tell about that. Let me complete the data first. And then mass of neutron, mass of neutron is 1.008665 U, and then mass of helium atom, atomic mass is 4.00260 U. Okay. So, this is the data given. Now, what is U? Atomic mass unit, and this atomic mass unit is mass of what? 1/12 of mass of neutral carbon atom in its ground state. 6 protons, 6 neutrons and 6 electrons making an atom in its ground state. So, that carbon 12 atom, mass of that divided by 12, that is 1 atomic mass units. If you write in terms of kilograms, this turns out to be 1.6605 402 into 10 power minus 27 kg. Okay. And if you write the mass energy corresponding to this mass, that is mass times c square. So, if you take this mass and multiply it by c square, this will be these many kilograms multiplied by 9 into 10 to the power 16, c square is 9 into 10 power 16 meter square per second square. So, multiply this number by 9 into 10 power 16, that will give you joules, that many joules. Convert that to electron volts, right. 1 electron volt is 1.6 into 10 power minus 19 joules. So, when you do that, that will be 931.478 mega electron volts. Okay. So, multiplied by c square and write in terms of electron volts. When you do this, 1 atomic mass unit corresponding mass energy is 931.478 mega electron volts. So, you can write this 1 U as this 931. Generally for calculations we take it 931, depending on what accuracy of calculation is required. This MeV by c square. So, another unit of mass, this is mass, 1 atomic mass, and this is mass, this many kgs. Okay. So, 1 U is 931.478 MeV by c square. So, this MeV by c square, this is another unit of mass which is quite regularly used in nuclear physics or particle physics. Okay. Similarly, GeV by c square, giga electron volt by c square, electron volt by c square, kilo electron volt by c square, and so on. Mass of electron will be 511 kilo electron volt by c square. So, energy by c square, that is taken as units of mass. So, let us come to this calculation. If we do this calculation, okay, let me remove this. If needed, we can write it quickly. So, you have the calculator. So, binding energy by definition is Z times mass of this hydrogen. Okay. Atomic binding energies are small compared to nuclear binding energy. So, we can use atomic masses in place of nuclear masses. So, this plus n times mass of neutron times c square and minus mass of, where is mass, where I am writing mass, here, Z into mass of this, mass of hydrogen atom. So, this takes care of proton part, this takes care of neutron part, and minus Zn c square. Okay, you can use atomic masses, atom, this atom with Z protons and Z neutrons and Z electrons. So, here also when you take a hydrogen atom, you are taking Z electrons, and here when you are taking this atom, you are taking Z electrons. So, they will cancel out, and difference in atomic binding energies is very small. So, this gives you, so this is by definition. Okay. If they are all separate, all protons are separate, all neutrons are separate, this would have been the mass energy. But then the nucleus as such, when it is bound, the energy is small, and the difference is binding energy. So, we are subtracting, this is binding energy. Now, put the data. In our case, what is Z? We have to calculate binding energy for this 4He22. So, what is Z? 2. Z is equal to 2. So, this is 2 into mass of hydrogen. The mass of hydrogen atom is here 1.007825 U plus capital N. What is capital N? How many neutrons are there? 2, right? 2 neutrons. So, 2 into mass of neutron is 1.008 665 U times c square and minus mass of that helium atom. Mass of that helium atom is given here 4.0000260 U times c square. Now 1 U into c square, you know, it is 931.478. So this is 2 into 1.007825 plus 2 times 1.008665 and minus 4.00260 and U into c square is 931.478 MeV. Okay, 1 U into c square is 931.4. So this is it. Now you calculate on your calculator and tell me the result. .3 MeV. Okay, 28.29, that's 28.3 MeV. So this is how one calculates binding energy from the known atomic masses. Okay. So for all different nuclei for which the atomic masses are known, one can get the binding energy in this fashion, and then go for that semi empirical mass formula and try to put proper values of those constants A V, A S, A C, etc. so that all these nuclei, the binding energies of all these nuclei are well produced by the formula also. Okay. So it is a fitting of data. An expression is given with some variable parameters, adjustable parameters, A V, A S, A C, these things we have to supply, they are not coming from theory. Right. The format, the form, that is coming from our theoretical discussions, but those constants we have to adjust, we have to supply, and that is done by looking at the actual data and then fitting, trying different values of those constants, and what set of constants gives me the best fit to the available data. So that is how those constants are determined, and when people do that, the values that come out, let me just state, is there in all textbooks. So that comes out to be AV, the first volume term 15.5 MeV, then the surface term AS, that constant 16.8 MeV. What is next? AC, Coulomb term, this is 0.72 MeV. Then asymmetry, this constant is 23 MeV, and AP, that is 34 MeV. The units should be in energy units. It is binding energy that you are writing. Binding energy is AV times capital A. Capital A is dimensionless, is number of nucleons. So this AV should be in energy units. So all these constants are in energy units. So with this you can fit the things better. Okay. Now we can understand certain properties of nuclei or certain systematics of nuclei using this. The first which I will be doing is the value of Z and N for a given nucleon number. We had discussed not any arbitrary combination of Z and N will give you a stable nucleus. Okay. So if you have say 100 nucleons, so you cannot have 20 protons and 80 neutrons and make a nucleus, a stable nucleus out of that, or reverse, you cannot do that. there are certain special combinations of Zn that results in a bound nucleus and a stable nucleus, right. So, how that Z and N can be obtained if the total nuclear number A is there, we can do it with the semi empirical mass formula. So, let us see, let us write the mass of the nucleus. Well, we had written binding energy, let us write mass of the nucleus. So, mass of the nucleus A x z will be Z times mass of this 1H1 and plus N times mass of neutron, let me write C square also, energy, this and times C square and minus the binding energy. So, minus AV times A and so on, minus binding energy, right. Again, that is the definition, that is how binding energy is defined. This is the mass when these protons, neutrons are all separate, and this is the mass when they are bound to a nucleus. So, it is smaller than this by this amount. So, let me write it once again, it is Z into mass of, let me write it from here, I need longer thing. So, this is equal to mass Z times mass of 1H1 and times C square of course, plus N times mass of N times C square. Okay. Then minus binding energy, remember it is minus. So, minus AV times A and plus AS times A to the power 2 by 3 and plus AC times Z minus 1 upon A to the power 1 by 3 and then plus asymmetric N minus Z whole square. Let me write it A minus 2 Z whole square by A, N minus Z, okay. N plus Z is capital A. So, N minus Z is A minus 2 Z, right. This is N plus Z and minus 2 Z will be N minus Z. Why I am writing in this fashion will be clear, and then plus delta, minus delta, right, minus delta, and this delta is AP divided by A 3 by 4 plus or minus or 0. So, what I have done, I have written this mass as a function of Z and capital A, mass number, total mass number and the atomic number. So, the idea is for a given A, what should be the neutron number and the proton number, that I want to know. So, for a given A, so A is constant. So, that is why I put A, and then proton number I will vary, neutron number will anyway vary because A is fixed. So, then I will try to see at what proton number, at what value of Z this expression is minimum. This is total mass energy, this is total mass energy of the nucleus. So, at what value of Z and corresponding N with a given A, at what value of Z this mass energy is minimum. So, that will be the stable nucleus. So, that will give me, that should give me the proton neutron composition for a given capital A. Now, to get the minimum energy, minimum value of this is mass energy of the nucleus with Z protons and N neutrons. To get the minimum value of this mass energy as I vary capital Z, keeping capital A constant, I should differentiate it and put equal to 0, right, simple. So, differentiate this and put that equal to 0. So, for minimum energy for a given A Z can be obtained by saying that this dm c square, whatever this dm c square over dz should be equal to 0. So, differentiate with respect to z. So, here you have a z. So, when you differentiate, it is mass of this hydrogen atom times c square, the c square is there, and okay, here you have n. So, let me write this as a minus z, right. Then it will be minus mn c square, okay, because I am keeping capital A constant and varying z. So, this n also I am writing a minus z and then differentiate with respect to z. So, minus mn c square, no z here, A is constant, then no z here, capital A is constant, z here. So, plus AC over capital A 1 by 3, let me write this first, then this is z square in minus z, z square will give me 2z and minus z will give me 1, right. Then here plus asymmetric by A, and here it is 2 times A minus 2z and multiplied by minus 2. Z you do not have z, in this delta you do not have z, okay. So, this is equal to 0, this should be equal to 0 and I have to get z from this expression, right. So, collect all z part on one side without z part on the other side. So, where are the z parts? Without z, here it is. So, 2 times AC over A power 1 by 3, correct, 2 times AC over power 1 by 3, z I will be taking common. So, this z I have taken, then where is z? Here it is, right, and this is 2 into 2 4 and into 2 8. So, plus 8 times this. So, plus 8 times A symmetric by A over all z terms I have taken. Now, go to the other side, the terms without z. So, this will be mn c square minus mass of this hydrogen atom times c square. So, I have taken this, I have taken this, and here it is plus AC by A to the power 1 by 3. So, this has been taken, and from here it is minus 4. So, plus 4 asymmetric and divided by A cancels, 2 times A minus 2z, yes, A cancels. So, what is left? That is all. 4 times, so minus 2, so on that side it becomes plus, into 2 is 4, and that is all asymmetric. Okay. So, z is equal to, you have noted those values. So, z is equal to mn minus m1h1 c square plus AC by A power 1 by 3 and plus 4 times asymmetric upon divided by 2 AC by A power 1 by 3 plus 8 asymmetric by A. Okay. Now let's take some numerical values. You have the data for this, just we solved the problem. You have the data for this. Mass of this hydrogen atom is there on your notebook. Mass of neutron you have. Just tell me how much will be Mn minus this M1H1 into C square. Make this calculation. You subtract this mass of hydrogen atom from the mass of neutron in atomic mass units and multiply it by 931. That will give you the value in mega electron volts. Mass of neutron 1.008665 minus mass of that hydrogen atom, subtract and multiply by 931.478. 0.78. Okay. So this portion is 0.7824 MeV. Now look at this part. How much is AC? 72 MeV, and this divided by A to the power 1 by 3. So it is going to be less than 0.72 MeV. Okay, whatever A you put. And this part, how much is this? 23. So 23 MeV. So what do you see? This is 0.78. That is less than 0.72, and this is 23. So this will dominate. Okay. Remember, we are trying to get this Z, number of protons, that can vary only in units of 1. So a difference of 0.01 and 0.02 and 0.001 will not matter. Number of protons cannot be 23.7428 etc. So anyway, we will have to get the nearest integer. So all those small variations do not mean much. So we can neglect this term and this term, and we can just keep this one. You can also look at the denominator. What are the relative things? This is AC by 1 by A3. So this is already there. This is already there. Okay. This will be around or less than 0.72 MeV. And what is this? Asymmetry is 23 MeV. But then it has to be divided by this capital A. Okay. This capital A. And we will be talking of capital A equal to 100, 200, 150, 50, etc. So if I take A equal to say 100, then this becomes 0.23 MeV, right. So here this asymmetry term was much larger than these, but here this may not be larger than this. This is only points or less than 0.72 MeV. So this is the range, and here it is 0.23, that is the range. So here you do not neglect this in front of this. This can be neglected in front of this. This AC can be neglected in front of asymmetric, but here this AC cannot be neglected in because of these factors here, this capital A here. So with these approximations, what is Z? Let me write once again. It is 4 times asymmetric this. So I have neglected all those 3 terms there, and here I am keeping both of them. So 2 AC over A 1 by 3 and plus 8 A symmetric over capital A, right. Simplify a little bit, multiply both numerator and denominator by capital A. So you have 4 times capital A symmetric and divided by 2 AC capital A to the power, I am multiplying both numerator and denominator by capital A. So, it is 2 by 3 and plus 8 times asymmetric, right. Now, divide by this asymmetric first, and let me also take 8A common from here. So, this is 4A asymmetric, I am dividing both sides, and I am also taking this or let me do it one by one. So, it is 2 times AC A power 2 by 3 divided by A symmetric plus 8. Is that correct? I have divided just by asymmetric numerator and denominator. So, numerator is 4A and denominator this becomes 8 and this becomes 2AC A power 2 by 3 divided by ACM, right. Now, you divide by 4 or take 8 common from here. Okay. So, how much it is, right. So, take that 8 common, then Z becomes capital A by 2 and 1 by 1 plus 1 by 4 AC by A power 1 by 3 AC over asymmetric and then A power 2 by 3. Okay. So, let us put values of AC and asymmetric also. So, it is A by 2 1 by 1 plus what is AC 0.72 MeV and divided by 4 into asymmetric. How much is asymmetric? 23. So, 23 here and then A power 2 by 3. Now, tell me how much is this factor? One plus 0.0078 and this multiplied by A power 2 by 3. Okay. Now, you can see for light nuclei where A is say 10, 12, 6, 8 like that, this factor is going to be very small as compared to 1, it is 0.0078 into. So, if A is small means 10, 12, 6, 8 of that type, then this factor is going to be very small and Z should be equal to A by 2. So, half the nucleons should be protons and half the nucleons should be neutrons. That is what we see in the real world. Stable nuclei, oxygen 8 8, carbon 6 6, right. So, light nuclei Z equal to N, whereas for heavy nuclei this factor will start coming up and then this will be less than A by 2, right. This is 1 divided by 1 plus this. So, once this becomes sizable, it is 1 divided by 1 plus something. So, it will be this factor will be less than 1. So, Z will be less than A by 2. So, neutrons will be more and protons will be less. That is what you actually see for heavier nuclei. When capital A is large, you have more neutrons and less protons. Let us do some calculations. So, calculate this factor for say A equal to 8. So, A equal to 8, tell me what should be Z from this formula. A is 8, 3.93. So, what should I write here? If you are getting 3.93, what should I write Z? Z cannot be 3.9, 4. So, 4. So, I have given you a value here, but this nucleus if you Let me talk something about this nucleus. What nucleus this will be? Z is equal to 4. What element it is? Z is equal to 4. Beryllium. So, this is an 8, A is 8. So, this nucleus is 8 beryllium 4 4. Since it has just come up, I am telling, not related to this chapter or this topic. This is highly unstable nucleus, and it decays into 2 alpha particles, right. It decays into 2 alpha particles, 4 He22 plus 4 He22, and lifetime is very small, something like femtoseconds, 10 to the minus 15 seconds or so. So, this is a very unstable nucleus, this particular one 4 4, very unstable, and this has good significance in in nuclear fusions in star. We'll talk about these things later. Now, let us come to the middle weight, say A is equal to 100. What should be Z? Make a calculation from this formula, A equal to 100. So, Z is 42. So, you can see if you have 100 nucleons for stable nucleus, this formula predicts that Z should be around 42, and what should be N? N should be 58, so that the total is 100. Let us do one more. A is equal to 235. Okay, do it correctly and quickly. A is equal to 235. This is uranium. I am hitting at uranium, around uranium. How much? 90. Yeah, Z is equal to 90. So, you see it is coming very close, right. You know uranium 235. Uranium 235 is Z is equal to 92. You have 238 uranium, 235 uranium, very useful material for all our electricity generation, all that. So, this formula, this semi empirical mass formula is able to tell you what Zn should be if you have a particular nucleon number. Okay. So, this is one good application of this. Now, look at this mass expression little more closely. Is it there? No. In terms of Z, mass in terms of Z, the one which you had differentiated, you have that formula, that expression, the one which you differentiated, dm by dz. So, look at that formula for m as a function of Z for a particular A. So, what kind of terms are there in Z? Is it a polynomial or you have something else? So, you have 3 type of terms there. Let me write. Say when you write mass of this x a z n, this will be Z times mass of 1h1 and then okay, let me put c square also, plus n times mass of n and then c square, this whole thing c square, and minus the binding energy, right. So, this will be Z times mass of 1h1 plus a minus Z times mass of n and then c square, and then minus binding energy will be plus AV capital A plus AS capital A 2 by 3 plus AC ZZ minus 1 by A power 1 by 3 plus ASIM A minus Z 2Z, A minus 2Z whole square by A and plus delta, plus or minus delta. We write plus there, so we write minus here, minus delta. So, you have a Z square term here and you have a Z square term here. When you write A minus 2Z whole square, you will have a Z square here. So that is the highest power in Z. Then you have terms proportional to Z, that is here, that is here, and that will come from here, and that will come from here, minus 2az. So you will have terms proportional to Z, you have terms proportional to Z square, you have terms proportional to Z, and all other terms are free of Z. This A times Mn, you do not have any Z here, A times you do not have any Z here, you do not have any Z here, and from here also you will get that A square, so there also you do not have Z. So you have three varieties, Z square terms will be there, okay, Z terms will be there, and constants independent of Z will be there. So it is like a second order polynomial. So this is like some A plus some Bz plus some Cz square. You have Z square terms, you have Z terms, and you have constant terms. Now this is a equation of a parabola. So if you look at the signs of all those things and draw this parabola, draw this mass as a function of Z. Okay, you can draw this mass as a function of Z. So it should be a parabolic shape. Okay, so let me take first that delta is 0. Okay, odd A case, odd A, although it does not matter, but let us take odd A case first, so that I can put delta is equal to 0, and this parabola Z this side and mass this side, and this parabola will be something of this sort. This is the shape of a parabola. Of course, the parabola can be in different orientations, but this particular one where you have all those values A, B, C, your parabola comes out to be something like this. Okay, and then you can, but the points are at integral values of Z. This is for a particular A, fixed A. This is for a particular value of A. So Z is different, A is same. You will have a point here, you will have a point here, you will have a point here, and then here, and so on. So this way you will get the points. So what are all these points? For a particular value of A, you can have different nuclei with different Z and corresponding N. These are called isobars. You know this word, isobar. A fixed, Z different, and therefore N different. So all these isobars are falling on this parabola, right? And all these isobar, one which will have lowest energy will be stable, and others will be radioactive, beta active, this side or that side, right. So that stability is another thing. You can have different nuclei with same value of capital A and different value of capital Z, but then of these nuclei, one perhaps or two perhaps will be stable and remaining will be radioactive. Either they will emit beta minus or they will emit beta plus particles or electron capture. So that nuclear stability will be our next topic, next lecture. Okay.